Okay, so in 5.3, we are talking about inverse functions. So if you'll find your notes for 5.3, okay. In 5.3, first we have to review what we know about inverse functions. This is from like pre-calculus and algebra 2, which is back a minute. And if we're being real honest, when we did inverse functions back in like pre-calc, we forgot we did them in algebra 2, so it just kind of is one of those things that gets forgotten a lot. Does anyone remember what inverse functions are or how we find them? Yeah, we learned it lots of different times, but maybe this will kind of give us a little review here. Graphically, an inverse, if you had a function that looked like this, the inverse of that was always the function that was symmetric to it over the line y equals x. Okay, so this would be like e to the x, and this would be like ln of x. And those are inverses of each other. Okay? In pre-calc, we did this in our functions unit. We did it towards the end of the functions unit. And we talked about how to find an inverse function.
Do you plug the x's in for y?
Yeah, it's like you switch your x's and y's. Yeah? So the way we find those is to switch x and y and solve for y. All right, blended together. Solve for y. Now, finding an inverse had quite the process because if it wasn't a one-to-one function, we had to restrict it and then find the inverse of like half of the function and all of the different things. So we just need to review a little bit about them before we jump into like how we're using them with derivatives, because without that, it is kind of one of those things that wouldn't make sense to you, okay? So a couple things about inverses that we did know. If you had points, like let us say I had the point on the function f of x and the point was 2, 3. If you then looked at your inverse function, given that the x's and y's switch, what kind of point would be on the inverse function? Or what specific point would be on the inverse function? Yeah. If your x's and y's flip, they have the exact opposite points on them. If they're symmetric across the line y equals x, their x's and y's actually switch, like on all the points. That's why like the e to the x graph goes through the point 0, 1, and the ln function goes through the point 1, 0. Okay, it's because everything about the x's and y's flip-flop. The other thing that we talked about flip-flopping on these is the domain and range switch. Domain of the first becomes the range of the inverse and vice versa. Now, algebraically, how we find one, let's say I gave you the equation y equals x squared plus 2. Our steps were always switch your x and y and solve for y. Now, this was one of those types that we would have to like restrict the domain on this, because if I looked at this, what does a quadratic look like? It's a U, yeah? So this is a U that it starts up to. Its inverse would be reflected across the line y equals x. So its inverse would look something like this. Is that inverse even a function? No. So what we did in these is that we always used the positive side. So on the original function, we essentially just said we're going to use the positive side of this quadratic, which means that its inverse has only the positive side of it as well. Well, what does that look like when we solve? Let's see. Okay? So when we solve this, we first switch our x and y. So what would that look like? X equals y squared plus 2. And if we're going to solve for a y, we have to first move what? Yeah, we subtract the 2. Got our y squared. How do you get rid of the squared? We square root. Now, usually when we square root, what do we put in front? Plus or minus, but because we restricted it to the positive side of the quadratic, we only use the positive side of the square root, okay, instead of both. And then we learned one other thing about inverses, and it was how to verify that two functions are inverse functions. So if we were told f of x is your original and g of x is your inverse, that does not look like the word inverse. We learned that you could do f of g of x, this is called function composition, as well as g of f of x. And in plugging one into the other, we knew that they were inverses if it worked out to x. Every time. Had to work out to x. Okay? So now, what we're going to be doing today is, of course, applying derivatives to this, because why not? That's where we're at. Okay? So, on the back, we are going to start finding the derivative of an inverse function. Now, on my unit circle, excuse me, to kind of give you the benefit of this, okay? We have a formula here. This is the formula for the derivative of an inverse function at a specific value. That value is called a. I'm going to first write down the formula for you, and then we're going to talk about why we need it and what it does for us. So our formula, the derivative of an inverse is 1 over f prime of f inverse of a. And if you want to write down in words like what you're specifically finding here, this is used to find the derivative of the inverse. Oops, can I spell? Inverse without knowing the equation of the inverse. Okay, so as you finish writing that, the point of this is, without this kind of formula, to do this process, you would have to take a function, switch its x's and y's, solve for y, that gives you the inverse function, plug your value into the inverse function, and then plug that value into the derivative of the original function. Okay? So on a question like example 1 here, without that formula, I would have to start off by saying, okay, here's my equation. How do I find the inverse of that equation? First, I would find the inverse by doing what with your x's and y's? Switching them. Okay, and we're not going to use this process, so don't write it down right now. Just follow with me. If I wanted to find the inverse of this, I run into the initial first problem when I switch my x's and y's. Because in order to find the inverse, what do I have to be able to solve for? Y. Can I solve for y there? I actually have no ability to find that inverse. A lot of functions we can't find the inverse actual equation of the inverse. So we'd kind of be like dead in the water right now and not able to find anything at all. However, if you can use this formula to kind of work around ever having that inverse equation, then you can still find those values. So the process for that is this. First and foremost, I'm going to write down my formula. I would like to find the derivative of f inverse at 3. So my formula tells me that that is going to be equal to 1 over f prime at f inverse of 3. Yes? Okay, so that's just my formula. But when you have things like within other functions, remember when we did function stuff in pre-calc and algebra 2, you start on the inside, right? So the first thing that I would like to find is f inverse of 3. Okay, because if I can start within there, I can then plug that into the derivative, which is actually not that hard to find. So first thing is just finding what f inverse at 3 is. That's saying in the f inverse function, when x is 3, what is y, right? Well, what do I know about the relationship with the inverse function and the original? In points. They flip, right? So if I need to know on the inverse function, when x is 3, what is y, how could I find that using the original?
Plug 3 into the original for x.
I can't plug it in for x, but I can plug it in for what? Y. So this question is the same question as on the original function, what is x when y is 3? If the points switch, right? Now, do I have an ability without finding the inverse function to solve where that equation equals 3? I do. So if I set this equation equal to 3, how would I go about solving it? Yeah, we need to get it all on one side, so I subtract 3. This gives me x squared minus 2x equals 0. How do I keep solving? Yep, we factor out an x minus 2. So we actually have two places where this happens. At x equals what? 0 and 2. Now, there's a very specific reason I went over that whole restricting thing on the previous page. We always keep the positive side of a quadratic. So which of these two x values are we actually going to use? 2. We're not going to use 0 because that would be on the left-hand side. There's 2 times it happens, we're going to use the right-hand side. All right, so if on the original function, when x equals 2, y equals 3, what does that tell us on the inverse? When x equals 3, y equals 2. All right, so now I know f inverse at 3. F inverse at 3 is the number 2. So let's proceed to the next step. The next step says I now need to do the derivative at that number I just found. The derivative at 2. Now this is not the derivative of the inverse, this is just the regular derivative. So what is the regular derivative of this function? 2x minus 2. And I can take that and plug in the number 2. If I do f prime at 2, I get back out what? 2. So my official answer to this entire question is 1 over 2. Now, how often is this used? About as much as you see it on the homework. There are 4 questions. It doesn't come up a lot. Comes up every now and then. It's a weird formula. This chapter has several weird formulas in it. Okay? But it's not that hard once you get to actually practicing it a couple times. Okay? So let us do that on the second example, which is also labeled example 1. If I want to find the derivative at f prime, or the derivative of the inverse at 0.5 or 1/2, I'm going to first set up my formula. 1 over f prime at the inverse of, now, I'm going to kind of think ahead here. I'm looking for a cosine of 2x formula. When it comes to trig, do we really think about 0.5? No, we think about what? 1/2. We're going to use 1/2. All right, so my first object is to find f inverse of 1/2. And to find f inverse at 1/2, I need to find the original function where the original function equals 1/2, right? So if I need to know where my original function equals 1/2, I'm going to go back to cosine of 2x and ask myself, where does cosine of 2x equal 1/2? Do we remember solving these kind of questions? Yes, no, maybe? Yes. These are the ones that we were like, big theta. We said to ourselves, where does cosine x equal 1/2? So does cosine of x equal 1/2? Pi over 3. Now notice they were very nice to us and gave us a very small range of values. So do I need to find another place where cosine equals that? No. I do not. However, this is not my answer for x. This is my answer for what? 2x. Therefore, to get my final answer, I do what? Divide it by 2. So my place of that is going to be pi over 6. So pi over 6 is our answer for both of those. All right, so step 2 then is to take this original equation we had and replace f inverse of 1/2 with pi over 6. Now we want to plug that into the what? The derivative. All right, so coming out to the side again. What is the derivative of our original function? So we're starting to get when we integrate, okay, the derivative of cosine is negative sine of 2x, but it's also multiplied by 2. The derivative of the inside. We're not going backwards. We're taking the derivative. Chain rule says derivative of the outside function multiplied by the derivative of the inside function. 2. Okay? So if I want to know f prime at pi over 6, that's negative 2 sine of what value? Pi over 3 when I multiply by 2. All right, what is the sine at pi over 3? Root 3 over 2. So my final value for that is negative root 3. So my final answer is 1 over negative root 3. Now, the one thing I will say about this, we had 2 examples here that we could solve algebraically for where does cosine equal 1/2 or where does this quadratic equal 3. There are a couple places, and I think you're going to see at least one in the homework, that it's not something you can solve algebraically real easily. And while I don't usually encourage you to play guess and check, most of those things, like where cosine equals something or where a quadratic equals something, can be solved with guess and check very easily. And usually they're very close answers to like 0. So like try 1, see if it works. Try -1, see if it works. If you cannot find algebraically where it equals a number, just play guess and check. And it doesn't take very long at all. I promise that. Okay? Told you it was a shorter lesson today. So